Hello to everybody, can you hear me? 1, 2, 3. Can you hear me? Is the sound okay?
We can hear you.
How is the sound? Can you hear me clearly?
Yes, it's fine, thanks.
The sound is okay. Okay, so you can hear me well, and the sound is okay. There is no problem with the sound. Okay. And you can see the PowerPoint I'm sharing with you, correct? Can you see the PowerPoint I'm sharing with you? Can you see the PowerPoint? 1, 2, 3.
Yes, we can.
Okay, thank you, Rosetta. You can see the PowerPoint. Okay, so in the Google Sheet file I have sent you, you would need to choose the time you are going to present your work. So you can choose the date you want. Let me send you the link again. The link is in the chat. You can present either on the 13th of May or on the 20th of May. Either on the 13th of May or on the 20th of May. You need to present in one of these two days. Okay, and you would need about 15 minutes each. Okay, let's make it 15 minutes each. So you can go to the Google Sheet and each team can choose a time they want to present. Okay, and they should write the time and their names. Okay, so if you want to present on the 13th, you write on the column I. If you want to present on the 20th, you write on column J. Okay, so write your name and the time you want to present. Okay, so but the people who wrote on the top are going to present first, and then write your name below each name. Okay, write your name below each name you can find over there. Okay, so Job and Maria have written their name. Below Job and Maria is going to be the second presenter. Okay, below Job and Maria is the second presenter. Below Valentina is going to be the next presenter. Okay, so below its name you need to write this is going to be the order you're going to present in the 2 days. Okay, so some people think if they present on the last day is better. It's not. Okay, so This is when you're going to present your work. Okay. So for your project, you need to prepare two things. For the project, you need to prepare two things. First thing is the project itself, and you would also need to prepare a PowerPoint presentation. You would also need to prepare a PowerPoint presentation. Okay. You would also need to prepare a PowerPoint presentation. So one more time, you would need to have your work ready by the deadline we have set, and for the presentation you would need a PowerPoint presentation okay, so you need to prepare a PowerPoint presentation as well.
Sorry, Professor, can I ask you?
Yeah.
Because I read on the paper that you sent yesterday that the deadline would be the 30th of May. But this means that if we have to present like the weeks before, both our project and the PowerPoint should be ready for the date in which our group is presenting and not on the end of May, right?
No, you will need the basic results by the day you're presenting. The idea, that's a very good question. The idea is you're going to present or either the 13th or the 20th. I'm going to give you feedback which you can take into account when you submit your final work. Okay. So when you present, you don't need to have all the work ready. When you present, you need to have just the basic results and the PowerPoint ready. Okay. So you don't need to have everything ready. You need to have just the basic results and the PowerPoint. Okay, the PowerPoint is significantly less work than the final project. However, I'm planning next week to have a one-to-one meeting with each group to see how your work is going to progress, because the idea is that you would need to do the work while the course is evolving. So I need to see what you're doing so far. Okay, so in the day of presentation, you need the PowerPoint ready. You don't need the full report. I'm going to schedule meetings with each group by the end of next week, so I can see how your work is evolving. Okay. Is this clear or not?
Sorry, Professor, you said that the meeting are gonna start in 2 weeks, right? Because you're gonna arrange the meetings by the end of next week, right?
Yes, in the end of next week, I'm going to have informal meetings with each group to see how their work is evolving. Okay, so if you need my help or anything else.
Okay, thank you.
Any more questions? So, have I sent you the... You have received the project, correct? Do you want me to send you the project again? Okay, questions. Zihavat, I will choose the country today. Okay, please don't choose the same country as the other people. So we have to present before the deadline. You have to prepare a PowerPoint presentation before the deadline. Yes, this is what I just said. You have to present your basic results before the deadline. I will give you feedback, and then you can take into account my comments for the final submission. Okay, so the idea of the presentation is to make sure that what you're presenting is fine, so you will get some feedback in order to avoid any problems. So it's the idea of presenting is to make sure that when you submit, everything is going to be fine. I'm just answering Job now. Georgia says, okay, thank you. Reza, is it possible to repeat what we do for presentation? I have some connection problems. Well, what I said is you need to go to the Google Sheet web page, the one I've sent you on the chat. Okay, the one I've sent you on the chat, and say whether you want to present on the 13th of May or on the 20th of May. Okay, so below each name, you can write your name, and this is going to be the order you're going to present. Okay, you need to prepare a PowerPoint slide of your for your presentation. You're going to present. I'm going to give you feedback. So we make sure that when you submit, you know that everything is fine. Okay, I'm just answering Reza now. I've sent you also the project again. You want me to repeat something here? You want me to repeat something? This lesson, I think, is recorded already. Salvatore, can you send the link again? The link for the Excel sheet, you mean? Google Sheet. It's the same one. I just sent it. Salvatore, I think the recording has started 28 minutes ago. Reza, I've sent you the link again. Okay. Any more questions? You want to repeat something here? Okay. Can I go back to quantile regression we were discussing yesterday? Can I go back to quantile regression that we were discussing yesterday?
Professor, last question. Like the first day, you tell us to download the color XY on for Gradle.
Yes.
But maybe because I have an old version, I couldn't find it on the extension of my Gradle. Could it be that is if I maybe download the last version, I could reach it through Gradle? Because
which version of Gradle are you running?
I think is the like 2 years ago one, maybe 2020.
It shouldn't be a problem. It shouldn't be a problem because Gradle is an add-in. So can you see my screen?
Yes, I do.
So you need to go to File, Function Packages on Server.
Mm-hmm.
Are you following me?
Yes, and then I simply search it for color XY or.
There you go, color XY, but which is here. So you're going to right click and then you have to install it.
Oh, okay, I found it. Yeah.
So if you install it, then you close this, and you go to File, Function Packages on local machine.
Okay, perfect. Thank you.
Okay. Once you install it, you can see it through the options View. But if you don't install it, you cannot see it. Okay.
Yes, thank you.
The Gradle version I'm using is 2022B. You can download the latest version. It's not something difficult. Okay. Any more questions? So, can you see the PowerPoint slides now? So, let me say which are the important bits here. What are the important bits here? Yesterday we were talking about quantile regression. What's the big advantage of quantile regression? And please make good notes so you are going to explain this very well in your project. So quantile regression is a way of examining the potential asymmetry that can exist in the relationship between two variables. One more time. Quantile regression can examine the potential asymmetry that can exist between two variables. Okay. Why we need quantile regression? We need quantile regression because standard OLS, standard regression, is focusing on the conditional mean. So an OLS coefficient is similar to the mean to the average value. It doesn't tell us what happens when a variable takes values that are relatively low. It doesn't tell us what happens to a coefficient when values are relatively high. Okay, so we need to quantile regression can help us determine what is happening when we have relatively high and relatively low values of the variable. So we are moving away from the mean. So OLS is the mean, the average response. Quantile regression is looking at the entire conditional distribution. Okay, so that's the difference between OLS and QR. So every time we have one beta hat for the OLS, we can have more than one in quantile regression. So in quantile regression, we can have a beta 1, a beta 2, and a beta 3. Okay, beta 1 would be valid for cases when the dependent variable is relatively low. Beta 2 would be valid for cases when the dependent variable is very close to the mean. Beta 3 would be valid when the dependent variable takes relatively high values. Okay. So one more time, OLS is measuring average responses, and we need to move away from the world of symmetry, linearity, and average responses. So OLS, symmetry, linearity, average responses. Okay, and QR, it's asymmetric, and you are looking at the entire distribution. Okay, so the quantile regression is looking at the conditional quantile functions. Okay, we can use it in both time series and cross-sectional context. And the dependent variable, we call it the response variable. And the big advantage of quantile regression is that it's robust to outliers. So we don't need what? We don't need what in quantile regression? Who is going to help me? We don't need what? Who is going to help me? When we say quantile regression is robust to outliers, it means that we don't need what?
Maybe we don't need the dummy variables. I don't know.
Very good. We don't need dummy variables. Well done. Who was that?
Theodore.
Theodore. Very good, Theodore. We have the same name. Very good. We don't need dummy variables, and is robust to non-normality also, compared to OLS regressions. Okay, so quantile regression is a non-parametric technique. The notation is different, so you have to be careful with the notation. It allows us to see what happens in the tails. When we say tails, we mean relatively high values of the dependent variable, the response variable, and relatively low. Relatively high and relatively low. A common use of the technique, you can use this in finance, you can use it in environmental issues. If you are interested, for example, in CO2 emissions, if you are interested in permits, quantile regression is a very powerful tool to use. Okay, this seems like a natural given that the models can estimate what's happening in the entire distribution. Quantiles we denote quantiles with the Greek tau, which refers to the position where an observation falls within an order series. So we ordered y, and t, when t is 0.10, this means that it contains 10% of the first 10% of the observations. Remember that observations are ordered. Observation y is ordered. That's why when we say 10%, 10% refers to what? To relatively low values of y. Okay, and when tau is 0.9, this refers to what? Relatively what? This refers to what? Who is going to help me? This refers to what? When tau is 0.9.
Does it refer to 90% of all our data?
Yeah, so it refers to relatively high values of. It refers to relatively high values of y. Okay. So quantiles refer to the values of y. Okay. These values of y are ordered, and we are cutting the distribution of y, and we are looking how the behavior between y and x changes when y is relatively high and when y is relatively low. Okay, when y is relatively high and when y is relatively low. Okay, so we can define the tau quantile. We usually call it qt, q tau, and the quantiles lie between 0 and 1. Quantiles lie between 0 and 1. So quantiles can go from 0 to 1. Okay, it can go all the way to 100%. Okay, quantile regressions model the entire conditional distribution of y given the expounded variable. So this sentence is a sentence that you can use in your project when you're going to explain why you need quantile regression. You say that quantile regression can model the entire conditional distribution of y. In your case, y, what is y in your case? CO2 emissions per capita. So why do you need quantile regression? You need quantile regression in order to investigate whether whether low CO2 emissions are different from high CO2 emissions per capita. Okay. You need to see the difference between high and low CO2 emissions. Okay, you need quantile regression can help you to check whether there's a difference between relatively high and relatively low CO2 emissions. Okay, do you want to repeat something? So I repeat this sentence. It's a very good sentence you can use in your project. When you want to when you want to explain, justify why you are using quantile regression. Okay. Any questions so far? Okay. So you need to remember that OLS is giving you the mean, the average response, and you can select quantiles of interest. Common choice is 5%, 10%, 25%, 50%, 75%, 0.9%, 0.95%. Okay. That's it. So if you want to explain what we're doing when we're running a quantile regression, a very simple but wrong justification is that what you're doing in effect is partitioning the data, and you're running separate regressions for relatively low values of y and relatively high values of y. Okay, this is the OLS equivalent of quantile regression. The problem is, well, the difference is that quantile regression does not partition the data. Quantile regression does not partition the data. What quantile regression does, it gives different weights to different observations. It does give different weights to different observations. Okay. So let's have a look in an example of quantile regression. We have a paper that was published in 2001, and it looks at the analysis of mutual funds, and it wants to see how a portfolio exposure to various styles varies with performance. So what the authors do, they conduct a style analysis by regressing returns of a fund on the returns of a large growth portfolio, the returns of a large value portfolio, etc., etc. So they compare the results of the OLS regression with the results of the quantile regression. By the way, this is what I did yesterday when I showed you the same thing with the UK data. The standard errors, you can also bootstrap them. If you bootstrap the standard errors, you get more reliable standard errors. You can also do this in your project. Okay, you can also bootstrap your standard errors to get more reliable results. Okay, so this is the table. You can do a table like this as well. So this is the OLS coefficients. Okay, so this is the OLS coefficient. This is the coefficient quantile for the 10%, quantile for the 30%, quantile for the 50%, quantile for the 70%, quantile for the 90%. So we have different responses depending on the quantile we are. Okay, so if you assume symmetry and linearity, your response is 15%, 14%, but when the dependent variable, the response variable is relatively low, you can see the coefficient is 35%. When the response variable, the dependent variable is relatively high, the response is 1%. Okay, and the median is also 0.01. This median, this is the median response. This is the one you can compare with OLS. So median response is the one you can compare with OLS. If you want to compare your median response, you have to do it by comparing the OLS coefficient, compare it with your quantile regression when tau is 0.5. Okay, this is what we did yesterday, by the way. Okay, let me repeat the analysis yesterday. Can you see Gretel now? Can you see Gretel?
Yes.
Okay, so I'm going to run quantile regressions for the simple variables. I'm going to run a quantile regression for the logarithmic transformation as well. Okay, so I can go to model, robust estimation, and then quantile regression. Okay, can I click OK here? Is everybody following me? Yes, can I proceed? Quantile regression. Okay, so CO2 emissions, GDP per capita, confidence intervals, and then I need to click also robust standard errors as well. With how many quantiles I want, let's say I'm going to choose 5%, 25%, 50%, 75%, 95%. Okay. Any questions here?
Yesterday, when we look at the tau graph, we also had to put robust standard error.
Yesterday we didn't click robust standard errors because I didn't discuss it. I discussed it today.
So what is the difference? The main difference? What?
The main difference is that when you take robust standard errors, you are taking into account potential heteroscedasticity or potential dependence in the error term. Okay, that's why in the notes we talked about bootstrap. Remember, I just said just 5 minutes ago. Yes. Is this Theodore? Is this Theodore I'm talking to?
No, Marco.
Marco. Very good point. Yesterday I didn't click on robust standard errors because I didn't discuss the relative point in the slides. Can I click OK now, Marco?
Yes.
Okay, Theodore, can I click it? Okay.
Yes.
Okay. So this is the quantile regression for for the levels of the variables. Later on, I'm going to do the same for the logs. Okay, so I'm going to click graphs, tau sequence, and GDP per capita. I can do the same with a constant, by the way, but my main interest is how CO2 emissions respond to GDP per capita. Okay, that's my main question. Okay, so here you can see that the difference between the average response, which is OLS, the blue line, is not that different from what is happening in quantile regression. Okay, now if you allow me, I'm going to do the same thing for the logs. So I'm going to do the log of CO2 emissions and the log of GDP per capita. Okay, so I'm going to run a quantile regression for the logs now. Okay, remember that I don't need dummy variables in quantile regression. I don't need to include square terms in quantile regression. Okay, I don't need square terms in quantile regression. So can I click OK now? Can I click OK? I forgot this one, obviously. Okay, so I can click OK now. You can see here that there is some type of asymmetry in the logarithmic case. The OLS coefficient is around 0.5, and the quantile regression is giving me different results. Okay, so you can see. So for instance, when CO2 emissions are relatively low, this is an interesting result. Okay, let's focus on this result a bit. I want to have the results of the OLS also. Okay, let's focus on these two results. Okay, this is important for your project. Okay, so one more time, let me remind you what we have here. So your attention for 5 minutes. So here I have the OLS results. The dependent variable is the log of the annual CO2 emissions per capita, and the independent variable is the logarithmic GDP per capita. So what we're saying here is, on average, if GDP per capita increases by 1%, the increase in CO2 emission is 0.49%. Okay, this is the average response. On average, because both of them are logs, 1% increase in GDP per capita leads to 0.49% increase in CO2 emissions. Okay, this is the average response. Now let's go to the asymmetric response. What are we saying here? We are saying that when CO2 emissions are relatively low, so when a country is relatively poor, in a sense, this is what we're saying, because a country has low CO2 emissions when you are poor, an increase in 1% increase in GDP per capita increases CO2 emissions by 0.41%. Okay, but and this is the important point, when CO2 emissions are relatively high, and CO2 emissions are relatively high when you are relatively rich, an increase in GDP per capita by 1% increases CO2 emissions by only 0.16%. So what are we saying here? We are saying that there is an asymmetric response. CO2 emissions increase more when you are poor. CO2 emissions increase less when you are rich. Okay. Is this clear? Is this clear?
Yes.
Theodore, Luca, do you want me to repeat that? So if I have to compare the OLS coefficient with the quantile coefficient, I have to go to the median response. And the median response is 44. Okay, which is sort of similar. Okay, it's sort of similar. Can you please tell me what you want me to repeat here? Can you please tell me what you want me to repeat here? Can you tell me what you want me to repeat here? Yes, 1, 2, 3. Who is talking? Okay, so let's have a small break. What time should we be back? We should be back at 5:10. Okay. So a small break to everybody. 1, 2, 3, can you hear me? Can you hear me? 1, 2, 3.
Yes. Yes, we can.
Okay. Do you want me to repeat something about the contact regression part? Do you want me to repeat something? Do you want me to repeat something?
No, thank you.
Okay. Okay, so I can delete all this. Okay. And we can move. We can move to the next bit. Which is where we discuss all the diagnostics for each model. Okay. To ensure Reza is asking to ensure that we input the data incorrectly correctly. Can I ask you to do it once? Come inside. How to bring them together. Okay. Okay, so let me show you. Okay. So what I'm sharing right now, I'm sharing the screen, correct? Can you please let me know whether you can see what I'm sharing?
Yes.
You can see. Okay. So this is the web page for the data. Okay. Let me send you the link again. This is the link with the data. Okay. So I will need to go here, download, and I'm going to download the CSV file here. Okay. So I'm going to download the CSV file here. Okay, I'm going to download the CSV file here. So I have the CSV file. I'm going to open the Excel file. Can you please tell me whether you can see the Excel file?
Yes.
Okay. So I'm going to put a filter on the Excel file. Okay. I'm going to put a filter on the Excel file, and I'm going to use only the UK data, because I'm using the UK data in my case. In your case, you can just check which country you are interested in. Okay. Now the UK data, they start in 7050, but you can see there are 10 years, every 10 years there is one observation. So I will start on 1800 because I get data every year. Okay. I'm going to copy this. Okay, and then I'm going to create a new Excel file where I'm going to paste this data. Now from this Excel file, what I need, I'm going to delete this data because they are not annual, they're every 10 years. So I'm going to delete this data. Okay, I need the annual CO2 emissions per capita. I'm going to put underscore so Gretel can read this data. Okay, I need GDP per capita also. I'm going to put underscore. And these three columns, I don't need them. I don't need the UK because I have only data about the UK. So I'm going to delete all this. So the only thing I need is to save this Excel file. Okay, so I can save this Excel file in the directory that I want. Okay, can call this book 1A or whatever. Okay, now once I've saved this Excel file, I can go to Gretel and open the file from here. File, open data, user file. And here, all I need to do is click on all files. So the file would be here. This is the file I just created. You need to click on all files. This is the file I have just created. Okay. So this is how you insert the data. You download the Excel file, you use a filter, you isolate the data, the country that you want to analyze. And then you insert them in Gretel. Is this okay? Benedetta, is this okay? Reza, are we okay? Are we okay with the data?
Yes, thank you.
Okay, Reza, the same. Okay, so this is done. I will need to put cancel, and I'm going to go to I'm gonna go to chapter 5. Okay, now you can see the slides, and these are the 5 assumptions we make. Okay, for each assumption you need to do the relevant test in your project. Okay, so this is this and this. The first assumption says that the average value of U is 0. The last test says that U follows the normal distribution, so you can test both things by looking at normality tests. Okay, normality tests. So for 1 and 5, for both 1 and 5, for both 1 and 5, the test we want to do is this one. for both 1 and 5, we have to do this normality test. Okay, for both 1 and 5, we have to do this normality test. Are we okay with this?
Yes.
Okay. Now, the second assumption is, we call the second assumption homoscedasticity, which we're going to talk about now. The test you have to do homoscedasticity is white. Let me show you in Gretel. The test for heteroscedasticity is this one. So for number 2, we do tests, heteroscedasticity, white tests. Okay, and the number 3 is no autocorrelation. The test in Gretel is here. The test in Gretel is here. Okay, so one more time, 1 and 5 from here, 1 and 5 from here, number 2 from here, number 3 from here. So these are the tests you need to do for all your models. Okay. Any questions? You want to repeat something? Okay, so we are okay. So let's see what happens. How do we test for the violations? What are the causes of the violations? What are the consequences of violation? And what are the solutions to these problems? So I talked about how we test for violations earlier. What are the causes and what are the consequences of the violations? Usually, the consequences of the violations are the coefficients are wrong, the standard errors are wrong, the distributions we assume are not appropriate, and the solutions we have to find to work around the problems and use alternative techniques. Use alternative techniques. So when we are doing diagnostic tests, we use either the F or the chi-square version of the test. The F test usually involves a restricted and a non-restricted model, and the F test usually implies that we are using the degrees of freedom. So the F test requires the use of degrees of freedom. Okay, the chi-squared version is also called LM test and has only one degree of parameter, a freedom parameter, which is the number of restrictions. Okay, the important thing is to remember that the F test is preferable for small samples. That's why we have to calculate the degrees of freedom, and the degrees of freedom is the number of observations minus the estimate coefficients. Okay, the chi-square is used when samples are relatively big. Okay, so in your case, because of the type of data that you have, you're going to focus on the F. So for you, the F versions are more appropriate because of the fact that your samples are going to be relatively small. Okay, your samples are going to be relatively small. So the first assumption is that the mean of the disturbances is 0. And the important thing is to remember that if we include a constant term, the constant term will will always gives us a 0 constant term. So if you have a constant term, assumption number one is usually satisfied. Okay, this is satisfied when we include a constant term. Now, the second assumption is very important. The second assumption says that the variance of the errors is constant. How do we call this assumption? Homoscedasticity. Okay, how do we call this assumption? Homoscedasticity. Homoscedasticity is when the variance is constant. When the variance is not constant, how do we call this property? When the variance of the errors is not constant, we call this heteroscedasticity. Heteroscedasticity. So for instance, in the graph, you can see that the variance here is relatively low, the variance here is relatively high. So here, this is evidence of heteroscedasticity. The variance increases. This is what heteroscedasticity means. The variance increases. This is what heteroscedasticity means. Okay. If the errors do not have a constant variance, we say that they are heteroscedastic. Okay. So heteroscedasticity can be identified through graphical methods, or you can test for heteroscedasticity using the Goldfield quant test or the white test. In our case, for your project, we're going to do the test of white. We're going to do the test of white. Okay. We're going to do the test of white. So I'm going to skip this test and we're going to do the test of white. So white general test for heteroscedasticity is one of the best approaches because it makes few assumptions. That's why we're going to focus on this. So we're going to start with a linear model. We're going to start with a linear regression. Okay. And we want to test whether the variance is constant. Variance is constant. So we take the residuals from the linear model. These are the residuals from the linear model, and we are going to run this auxiliary regression where the residuals squared are going to be regressed on the independent variables and squared values of the independent variables and the cross products. Okay, so we take the residuals, and we regress them on the independent variables, the squared independent variables, and the cross products. Okay. We take the R squared from the auxiliary regression, and the test statistic is T times R squared, where T is the number of observations, and R squared is the R squared from the auxiliary regression we saw in the previous slide. Okay, let's see how we do this in Gretel. Okay, now we have run model 4, which is the logarithmic model. Okay, so the logarithmic model is this one. So from here I need the residuals and I need to run the auxiliary regression. So I would need to go to the option tests, heteroskedasticity, y-test. Now, because Gretel is usually printing all the results for all the diagnostic tests below, let me start with the question with diagnostic number 1, where I'm going to test for the normality of residuals. This is diagnostic number 1. Okay, these are the results. Even if I close them, the results are going to be here. Okay, so are the residuals normally distributed? No, because the p-value is 0. The null hypothesis is here. Errors are normally distributed. The p-value is 0. The p-value is 0. Okay, now let me go to diagnostic number 2, where I'm going to test for heteroskedasticity. Test heteroskedasticity y-test. Okay, test heteroskedasticity y-test. So I'm gonna click heteroskedasticity test. You can see this is the auxiliary regression. This is the regression that we've done here. Okay, and the test statistic is T times R squared. R squared is 0.24 times 2 to 1. Okay, so this number here is 221 times 0.24 will give us 53. And the p-value of this 53 is 0. Now the null hypothesis is that the disturbances are homoskedastic. The disturbances are homoskedastic. So in this case, the disturbances are homoskedastic. So in this case, what I'm going to do with this null hypothesis? What am I going to do with this null hypothesis? The disturbances are homoskedastic and the p-value is 0. Should I reject or not reject the null?
Reject.
So we're going to reject. Is heteroskedasticity present in my model? Is heteroscedasticity present in my model? Yes, it is. You can see the test has been printed here. Okay, so if I do all the tests in Gretel in the specific order I'm doing now, you can copy and paste them in your project. Okay, so what happens if there is heteroscedasticity? For example, in my case, heteroscedasticity is present. OLS estimation are unbiased coefficients, but they're not blue. So the standard errors are inappropriate. If the standard errors are inappropriate, I cannot use t-test. I cannot use the t-statistic. I cannot use the p-values. I cannot construct confidence intervals. So all these are wrong. Okay, so I need to update the standard errors. I need to update the standard errors. To take heteroscedasticity into account. To take heteroscedasticity into account. Okay. So, how can we reduce heteroscedasticity? You can reduce heteroscedasticity by taking logs. We have already done this, but taking logs reduces heteroscedasticity. The second thing we have to do is use standard errors that take into account heteroscedasticity. For your project, you need to do this. Okay, let me show you how we can do this. Okay, so here I have found that there is heteroscedasticity. How do I know there is heteroscedasticity? Because the p-value is 0 and the null hypothesis is that heteroscedasticity is present. The p-value is 0 and the null hypothesis is that heteroscedasticity is present. Okay. So I'm going to go to edit, modify model. Okay, now you're going to follow exactly the same steps if you do find heteroscedasticity in your data. Okay. So in this case, the p-value is 0, heteroscedasticity is present, so I have to update the standard errors. These are the standard errors. I have to update them. So I need to go to edit, modify model, and the only thing I have to do is click on robust. Okay, the only thing I have to do is click on robust. And the new standard errors that is going to be created take into account heteroscedasticity. So the standard errors, the coefficient used to be, the coefficient was 2.57, it's still 2.57. The standard error though used to be 0.32, now it is significantly higher, is 0.83. You can see the standard error that takes into account heteroscedasticity has increased significantly. has increased significantly. Okay. Has increased significantly. The coefficient used to be 0.49, it's still 0.49. The standard error used to be 0.03, now it is 0.91. It has increased significantly. Now, if I go and do a wide test again, the result is going to be the same. There's going to be no change in the result. The result is not going to change, the result would be the same. But now this is not an issue because the test is going to tell me whether heteroscedasticity is present or not. If heteroscedasticity is present, it does affect only the standard errors, not the coefficients. Have my new standard errors account for heteroscedasticity? Yes. So I don't need to do a test again. If I do it, the result is going to be the same, but this is something that I'm not interested anymore. Okay, so the result is still the same, but this is not going to affect something that I'm doing. These standard errors take into account heteroscedasticity, so I don't need to test again. Is this clear? Are we clear?
Yes, just a question. Where can we find this set of slides?
These slides, I think I've sent you on the chat. Let me send you the slides again.
Okay, thank you.
They are not on the chat.
I think yesterday you sent chapter 3 and 4, but not 5, I guess.
Yeah, they are already here. If you go to the files, you're going to find them, but I send them again. Okay. Did you follow what we have done with heteroscedasticity?
Yes, thank you.
Do you want me to repeat something about heteroscedasticity?
No, I'm good, thank you.
Okay. The important thing is to remember is that when you update the standard errors, the new standard errors are going to be significantly, they're going to be increased. You're going to get wider standard errors. You're going to get wider standard errors. Okay. You're going to get wider standard errors. Any questions? You want me to repeat something?
All clear, thank you.
Okay. So you can do exactly the same in your project. So if I go back to the slides, the new standard errors are going to be increased. So this will make us more conservative. Why? They are going to produce wider confidence intervals. Let's see it here. So let me go here, confidence intervals here. This is without heteroscedasticity. This is with heteroscedasticity. Okay, so the confidence intervals without heteroscedasticity is -321 to -192. Here you can see it's significantly wider. It goes from -4.22 to -0.91. The coefficient beta without heteroscedasticity goes from 0.422 to 0.56. With heteroscedasticity, it's wider, you can see, goes from 0.31 to 0.67. 0.31 to 0.67. Is this okay? Can you see the result, the difference in the confidence intervals? So this is without, this is with. Okay. Any questions? Anything you want to repeat? Now, let's go to autocorrelation. Autocorrelation requires, autocorrelation is present when we have a time dimension. So, okay. So here I'm measuring time, and here I have my variable yt. Okay, so autocorrelation is something we observe when our variable changes in the time dimension. This t refers to time. Okay, to the time dimension. If you want to take the lag of a variable, this is a lagged variable. Okay, what you do is you create a lagged variable. So from September 89, if y is for October 89, if yt is 1.3, yt minus 1 is 0.8. Where is this 0.8 coming? This is the lagged value. This is the value in the previous period. Okay, and delta yt is yt minus 1. Okay, what is delta yt? Delta yt is usually the growth rate of a variable. The growth rate of a variable. Okay, so in the dimension of time, we're gonna have yt, which is the variable that evolves in time. Yt minus 1 is the lagged value of the variable that evolves in time, and delta yt is the growth rate of a variable. Is the growth rate of the variable. Okay. Any questions? So what is autocorrelation? Autocorrelation is the violation of the assumption that two error terms are correlated. Okay, so this means no autocorrelation. In other words, this means that there is no pattern in the errors. There is no pattern in the errors. So the errors refer to the population. We don't have the errors, we have the residuals that refer to the sample. So this is about the sample, this is about the population. If there are patterns in the residuals, we say that they are autocorrelated. Okay, we say that they are autocorrelated. Now, this is UT plotted against UT minus 1. This is an example of positive correlation, or if you plot correlation over time and you get this type of things, This is a case of positive correlation. Positive autocorrelation is usually visible when you observe a cyclical residual plot over time. Positive correlation means UT is positive correlated with UT plus 1. So what happens yesterday is affecting positively what is going to happen today. What happens yesterday is going to affect positively what is going to happen today. Negative autocorrelation is indicated by alternating pattern where the residuals cross the time axis more frequently than if they were distributed randomly. So you can see negative correlation, UT minus 1, negative correlated. So if yesterday something was positive, today it's going to be negative, tomorrow is going to be positive. Okay. And no autocorrelation, something is random, no patterns, random. Okay. Now, if you have residuals with no autocorrelation, that means that your model is good. Your model is good if there are no patterns in your model. If there are no patterns in your model. Okay. How can we test autocorrelation? We test autocorrelation with Darwin-Watson. Darwin-Watson, and please make a note of this, is a test of first-order autocorrelation. So it looks at the relationship only between t and t minus 1. Only the relationship between t and t minus 1. So I can only look at the relations between today and yesterday. I cannot look at the relations between t and t minus 2 with Darwin-Watson. So only one lag with Darwin-Watson. The null hypothesis is no autocorrelation. No autocorrelation of first order. No autocorrelation of first order. And the alternative is there is autocorrelation. Now, Darwin-Watson, if it's close to takes values between 0 and 4. If Darwin-Watson is 2, that means there is little evidence of autocorrelation. The problem with Darwin-Watson, it has 2 critical values, and sometimes there are areas that the test is inconclusive. When the Darwin-Watson is around 2, there is no autocorrelation. When it's 0, positive autocorrelation. When it's 4, negative autocorrelation. Let's have a look in Gretel. Gonna close this. Go to the simple model. Darwin-Watson is here. You can see the value is very close to 0, so I'm probably here, positive autocorrelation. Okay, however, I need the exact critical values, and these critical values can lead to inconclusive results. Now, we are lucky because Gretel has a way of calculating a p-value for the Darwin-Watson. And the p-value in Darwin-Watson is available from the option tests and p-value. Tests and p-value. Okay. So, is there positive autocorrelation in this specific case? So the null hypothesis is positive autocorrelation. has a 0 p-value, so I reject it. Negative correlation, it seems to be present. So here, sorry, no. This is the alternative hypothesis here. I'm wrong. So I reject the alternative, and there is evidence of positive autocorrelation. Okay, because this is H1. H0, there is no autocorrelation. So here we have evidence of positive autocorrelation. Okay. The conclusion here is that we have evidence of positive autocorrelation. Why? Because in this case, I reject the null. The null says no autocorrelation. Here, I cannot reject the null. The null again says no autocorrelation against the alternative that it's negative. So from this result, my conclusion is that there is positive autocorrelation. Okay. One more time, I repeat, we get it from here. Do you want me to repeat something? You want me to repeat something? Shall we do a small break? And we're going to be back at 6:15. We are back. For Darwin-Watson, you can do it with both the model with the breaks. This is the Darwin-Watson for the logs. You want the Darwin-Watson for and do the Darwin-Watson also for the linear model. This is the Darwin-Watson for the linear model. This is the Darwin-Watson for the logs. So you have to do a Darwin-Watson test for all your models. Any more questions?
No, thank you very much.
Okay, so let's have a small break and then we'll continue after the break. 1, 2, 3. So let me continue with autocorrelation. Let me repeat that autocorrelation is important in the time dimension. And we have two tests for autocorrelation. One test is the Darby-Watson test, which is a test for first order correlation, autocorrelation. When we say first order autocorrelation, we mean the relationship between t and t minus 1. And we have the Bross-Godfrey test, which is higher order correlation, where we can see whether t is related to t minus 1, t minus 2, etc. Okay, so another test for autocorrelation is the Bross-Godfrey. The Bross-Godfrey test is a test for higher order autocorrelation. Okay, so we can see whether UTAF is related to UT minus 1, UT minus 2, UT minus 3, etc. The null hypothesis is that all the rows are 0, so the null hypothesis, no autocorrelation. And the alternative is that there is autocorrelation. So how do we perform the test? We estimate the linear regression model. We obtain the residuals, and we regress the residuals on lagged values of the residuals. We take the R squared and we multiply T. T is the number of observations. R is the number of lags. And R squared is the R squared of the serial correlation of the auxiliary regression. So if the test statistic exceeds the critical value, then we reject the null of no autocorrelation. Let's see how we can do the test on Gretel. Okay, let's see how we can do the test on Gretel. So the test can be done from here. Test autocorrelation. Okay. So test autocorrelation. How many lags? Here I have annual data. So let's put up to 2 lags. Okay, so this is R. R is 2 here. Okay, this R is 2. And these are the results. This is the auxiliary regression. R squared is 0.95. If you multiply 200, it's 2 to 1 minus 2, so 219 times 0.95, you're gonna get 212, and the p-value is 0. Okay, the p-value is 0. Even if I close this one, the test results are gonna be here. Okay, and the p-value is 0, as you can see. So the null hypothesis of no autocorrelation in this case is rejected or not rejected. The p-value of 0, so the null hypothesis of no autocorrelation is rejected or not rejected. Who is going to help me?
Rejected.
So the null hypothesis is going to be rejected. So there is serial correlation. There is autocorrelation. Now, if autocorrelation is present, and in my example, this is the case, this is indeed the case, we have autocorrelation. So the coefficient estimate using OLS are going to be unbiased, but they are going to be inefficient. So they are not blue. So if the standard error estimates are inappropriate, then we are going to make wrong inferences. The conclusions are going to be wrong. R squared is going to be inflated. So if there is autocorrelation, all our estimates seem to be wrong. So what can we do to remedy autocorrelation? If we know the form of autocorrelation, which is not likely, we can use a GLS, generalized least squares. But this remedy assumes that we know the form of autocorrelation. In most cases, we don't know the forms of autocorrelation. The modern approach we're going to follow here is that the autocorrelation presents an opportunity to modify the model. So if there is autocorrelation, we need to modify the model. And when we say modify the model, in our case, we have something like this. We're going to include yt minus 1 in the model. So when we say modify the model, we're going to include a lagged value of the dependent variable to remedy autocorrelation. Okay, so let's see how we can do this. So one more time, do I have autocorrelation in my case? Yes. It's here, it's clear from this p-value here. So what should I do? I need to include a lagged value of this dependent variable. Okay. Can you see the slides? Can you see Gretel? Can you see Gretel?
Yeah.
Okay, so I'm gonna click Edit, Modify Model. I would need to click on lags because I need one lagged value of the dependent variable. So I'm going to click lags of dependent variable, one lag, and then I'm going to click OK. Can I click OK? Is this clear? You can see the lagged value here. I'm going to click on robust standard errors because I know there is heteroscedasticity from the previous test I have done. Okay, so robust standard errors, lags, and then I'm going to click OK. This is the lagged value. How did I insert the lagged value from here? Can I click OK?
Yes.
Why did I click on the robust standard errors here? Why did I click on the robust standard errors? Because because I had evidence of heteroskedasticity in the past. Is the lagged value of the dependent variable statistically significant? Is the lagged value of the dependent variable statistically significant? Is the lagged value of the dependent variable statistically significant?
Yes.
Okay. It is significant, so now what should I do here? I should do a test for normality. I'm going to delete all this. I'm going to do a test of heteroskedasticity. Going to delete this. I'm going to do a test for autocorrelation. I'm going to delete all this. Why? Because the results are here. Are the residuals of this model normal?
No.
No. So normality is rejected. Do we have heteroskedasticity? Do I have heteroskedasticity?
A bit, maybe.
A bit. We don't have it to 1%, but we have it the 5 and the 10. Is this a problem? No, because my standard errors take into account heteroskedasticity. Okay. Autocorrelation is present. Yes, autocorrelation is still present. I have inserted one lag and autocorrelation is present. Okay, so I need to modify the model again. Okay. Let me insert the two dummies here to see if something happens. Now the dummies here are significant. The dummies are significant. Okay. The dummies are significant. Let me now do the test for normality. I'm going to delete this. Let me do the test for heteroskedasticity. I'm going to delete that. Let me do the test for autocorrelation. Normality with the dummies, it's still the p-value 0. Okay. Although the test statistic went from 900 to 300. Heteroskedasticity is still present, but it's not a problem because I have taken this into account. What about autocorrelation? What about autocorrelation?
We accept the null hypothesis that there is no autocorrelation.
So we cannot reject the null hypothesis that there is no autocorrelation. How did I solve autocorrelation? Look, here I had autocorrelation, here I don't have autocorrelation. What's the difference between this model and this model? The two dummies is the difference. With the two dummies, you can see that log GDP is significant, the two dummies are significant, and the CO2 emissions lag is also significant. Okay, the adjusted R-square has gone to 98%, and the Akaiki is more negative. Any questions? Did we solve the problem of the correlation? Yes. How did we solve it? We solved it with a lagged value on the left-hand side and with the two dummies. So the dummies You have to experiment with the dummies depending on the country that you have chosen. Depending on the country that you have chosen. Okay. Can you please tell me what you want me to repeat? Can you tell me what you want me to repeat?
Yeah, so the dummies, we add the dummies only in case everything we have done before, including the lags, including the robust standard error, doesn't correct the autocorrelation.
Yes, but also look, here I'm looking at the residuals of the model without the dummies. Can you see on the left?
Mm-hmm.
So can you see it's clear that there are 1, 2, 3 dummies that I need to use? Can you see these outliers? This one is clearly an outlier. This is 1927. This
So
is
probably
1926.
if we have outliers, even if we have
Probably I would need to do one more outlier, 1927. Let me go to analysis. Let me go to the residuals. Can you see? 1, 2, 3, 4. I have created 2 dummies, and this table is telling me that I should create 4 dummies. One for 1921, one for 1922, one for 1926, one for 1927. I repeat that you need 1 dummy per point. You cannot do 1 dummy for all of them. You need 1 dummy for 21, 1 dummy for 22, 1 dummy for 25, 1 dummy for 26.
So, for example, I chose Germany, and I have 2 outliers, 2 very far points, based probably because of the war, because it's in
it's probably the Second World War.
Yeah, so I will have to use 2 dummies, basically.
Yes.
Okay.
Exactly. So if you have 1 dummy in 1945, for instance, it's going to, if you include the dummy, the dummy is going to do 2 things. It's going to increase your adjusted R-squared significantly, and it's going to make all your diagnostics behave better. It's going to make all your diagnostics behave better. Okay. Any more questions? Anything you want me to repeat? Do you want me to repeat something? Anything?
Professor,
yes.
Can you explain the coefficient value of these dummies?
The coefficient
how I can interpret the coefficients of this dummy?
Okay. So in 1921, the coefficient is minus 4.01. So in 1921, only this specific year, we had a significant reduction in annual CO2 emissions by 0.401. So this year, because of the war, because this is a year of there was war in Europe in 1921. There was a significant reduction in CO2 emissions. Okay, only this year. In 1926, only for this year, there was a reduction of 0.6 in 1926. Okay, now the First World War ended in 1918, but this 1921 reduction could be related to what has happened in the First War or in the subsequent wars that the UK was involved in. Okay. So
Okay, thank you.
the coefficient of the dummy is telling us what is happening to this variable, the dependent variable, on this specific year. So this in the 21 we had a reduction of minus 0.04. In 1926 we had a reduction of minus 0.61. Were these reductions significant? Yes, they were. Okay. If I go to the graphs, obviously, you're going to see that there are still some outliers left. Okay. There are still some outliers left. If you go to analysis influential observations, also you can see that some observations are more influential than others. There are these two observations. Okay, you can do it from here. Bootstrap is a way of bootstrapping the standard errors. You can choose a coefficient, and this is going to bootstrap your standard errors. For example, let's assume that I'm interested in this coefficient, GTP. I can do while bootstrap, and this is going to give me the empirical distribution of the coefficient. I can do this from the option bootstrap. Okay. Anything you want me to repeat? You want me to repeat something? Do you want to repeat something? No? So why do you want to include lags in your regression? When we say lags, we mean yt minus 1 on the right. The lag would measure the inertia of the dependent variable, it would measure the overreactions, and it are going to help us get rid of autocorrelation. Help us get rid of autocorrelation. Okay. So the next step is to do models in differences. Okay, we're going to talk about this tomorrow, but if I go to the, let me go to the project. Let me go to the project. We have done so far, we have done the linear model, we have done the non-linear model, we have done the logarithmic model, and we have done the quantile regression. The only thing we have not done is first differences. So far, we also know to do for each model, we need to comment on the t-test and the p-value, and we need to produce confidence intervals and f-tests for each model. For each model, we want autocorrelation tests. So for each model, you need to produce a Darwin-Watson test and the p-value of the Darwin-Watson, and you also need the Bross-Godfrey test. If there is autocorrelation, you need to try and solve it. Okay, you need to try to solve it. Okay, are there guarantees that you can solve all the problems like in my case? No, there are no guarantees. The only thing is that you have to show that you have tried to solve it. You don't need to solve it. You have to try to solve it, okay? Because sometimes it's difficult, but the important thing is to make an attempt to solve it. If you put if you try the lags and the dummies, autocorrelation should reduce significantly. For each model you're estimating, you need the heteroscedasticity-wide test, and we're going to do the misspecification test later on. You need to do this test for misspecification for each model. You have to try outliers for each model to see whether you can delete them by including a dummy variable in each case. Okay, so this is the graph so far. These are where the data are. The data usually are in this link. The only thing I would like to add is that in the introduction, it's a good idea to discuss why you are expecting CO2 emissions and GDP to be related. In the introduction, you can discuss why you are expecting GDP and CO2 emissions to be related. Okay. What you know from theory about the relationship between CO2 emissions and GDP per capita. Questions about your project? Has everybody chosen a country? Everybody has a country. So Maria and Carolina have India. Salvatore and Ataul have Portugal. Valentina and Carolina have Indonesia, but Valentina and Carolina, they haven't written how many data points they have. Salvatore and Ataul, you can use interpolation to get more data because CO2 emissions are 151 and GDP is 149. Maybe you can interpolate GDP data and get 159 observations. Valentina and Carolina, you need to write how many observations you have for Indonesia. Job and Maria, they have Italy, but they haven't told me how many observations they have. Hugh and Guglielmo, they have Australia, very good. Federico and Danielle, South Africa, but they haven't told me how many observations they have. Sergio and Chiara, Colombia, 97 observations, this is fine. Theodore and Eduardo, they have Denmark, 176, very good. Benedetta and Giuseppe, they have US, 200 observations, okay. 220 GDP. It's not 2018, it's 218. There's a 0 there. Nihat has Singapore, but there is no data about how many observations you have. Francesca, France, you need to write how many observations you have. Marco has Germany, which is you need to try there with the dummies because of the war. Japan also, you need to try the dummies because of the work. Luca and Andrea have Japan. They need to tell me how many observations they have. Tatiana has Norway. How many observations for Norway? I cannot see. Petra and Rebecca, they have China and South Africa. Very good. But please tell me how many observations you have. Pietro and Simone, they have Sweden. 180. Very good. Lisa and Chiara, they have Costa Rica. How many observations? Is not clear. Chiara and Vanya have Mexico, 130, okay, very good. Kirer and Ruggiero, they have Spain. How many observations? I cannot see. Reza and Mehrad, they have Netherlands, 172, very good. Switzerland also. Aya has Qatar, 70 observations. Rosita and Christina have China, but how many observations they don't tell me. Sofia and Lurpo, they have Finland, 161. Ilari and Ezgi, they have Turkey, 156, very good. Federica and Sylvia, Iceland, 69. Luxembourg, Fiore, Sabrina and Isabel, no observations. Ziyafat has Armenia, Azerbaijan, 30 observations is not enough. So Sifayat, you need a different data set. 30 observations are not enough. You need to find another country. Okay. So I'm gonna write here, you need another country. Because you have to, your observations are limited. Any questions? Any questions?
Professor, sorry, I have a question, not about the project, but about the recordings.
Yeah.
Since some of us cannot access to the recording, I was wondering if you can please upload them to the files. Yes, oh, there are, okay. I don't know why we can not find them on files, but you already uploaded them on files, all the recordings.
I will try to check.
Okay, thank you very much.
Guglielmo, can I do the project if I don't do the partial exam? I think you need to ask Professor Fanelli about this. Okay. I think you need to ask Professor Fanelli. Okay. Other questions? You want me to repeat something? Do you want me to repeat something? Well, you would need more than 60 or 70 observations. Your GDP data is only 30, so you need to find something more. Other questions? Okay. If there aren't any other questions, then I think you should have some rest. Thanks for attending today. And then I'm gonna see you on Monday again. Have a nice weekend. Have some rest. Thank you, Theodore. Have a nice weekend, and then we're gonna meet on Monday. Enjoy your weekend. Have fun. Do not work too hard during the weekend. You don't need to finish the project this weekend. You can finish 90% of the project, but not all of it. Only 90% is enough. Okay. Bye-bye to everybody.
Thank you. Goodbye.
Thank you. Bye.
Bye-bye.